introduction, Amra. So I'm not sure I said very fast, but fast is okay for me. And from the punchline, you see, I already feel a bit like a hypocrite because my previous talk was like, oh, the optimization is too slow. We need to do something entirely different, a search-based algorithm. And now I'm presenting something about optimization. So for the Q&A session, tell me if you see the connection and how to merge these works potentially. Right, so this work is also the source of this hypocrisy. It was a different co-author. First author of the work is Fabian Geier, who's with Airbus Munich and TU Munich. And this paper was presented at Infocom this year. I brought again the original slide set that was created by Fabian, but I cut out the network calculus background. So the title is Network Synthesis Under Delay Constraints, the Power of Network Calculus Differentiability, and I'll show you how that leads to optimization. All right, so the motivation for this synthesis is that real-time network synthesis is quite a complex task. But what do we want to do? We want to meet hard real-time deadlines, so we want to write delay guarantees that are formally validated. And of course, our tool of choice is the network calculus. But on the other hand, secondly, we want to optimize something in the network, some parameters that go into a configuration, and that might be the paths flows take. And if there are alternative paths, then the flows, they have very different interaction patterns impacting the derivation of what I called before the algebraic term that bounds the analysis. And you can imagine if you have a lot of flows with a lot of paths, what happens is that just explodes combinatorially. So we have an explosion in, and here's again this metric I use so often for the trade-off, an explosion in the time it takes to optimize the network. I'm talking a lot of paths because this is the example we take in this picture, but there could be other things to optimize, like scheduler parameters, like the weights and weight around robin, or whatever can be made fit into this framework. So this statement here is a bit substantiated with the figure on the right, where we went the naive way and did a mixed integer linear program formulation of finding good paths that have minimized the average delay bound. X-axis is sum of the number of servers and flows. So we are merging these things together to get a simple metric of size of networks, and left the execution time again, exponential scale. And we see scaling is not too well. The main contributions of this paper is an analysis, a path from the problem statement to the solution that scales better. Yeah, for most parts, if the networks are really small in this metric, then the overhead of going our new path is exceeding the overhead of the old computational path. So that should not remain unmentioned. So we go the path, this overhead creating paths, to demonstrate how to differentiate the network calculus bounds expression. So this is the symbolical algebraic expression that ends with simply some leftover service curve computation, this time not FIFO, not with the FIFO parameter, but arbitrary multiplexing because it's a bit easier. The arrival curve of the flow we analyze, and the horizontal deviation to bound the delay. So we illustrate that, and here is the optimization that gets us the benefit. After having differentiated this term, we can use gradient-based optimizations. They are known to be faster, and we show that we can use that here, benefit from that as well. And being faster then results in scalability for analyzing larger networks where the metric for the x-axis, if we just restrict the flows, becomes way bigger. All right. This is the outline. This is what I cut out mostly, the introduction to network calculus. I just want to, again, start with Jean-Yves' book, where we have this set of operations. Despite this here, we define ourselves for a bit more for a bit more ease of notation. So we have all these min plus algebraic convolutions that we want to have in for PMOO and PBOO effects, deconvolutions for output bounding in the as it is required in the feed-forward analysis, where we have to bound the arrivals of cross traffic. And we compose them by some rules to what we call the analysis separate flow I showed before, and PMOO, the effects that really tighten our bounds. Now we have this min plus algebraic definition, but we cannot put the min plus algebraic term into our solver just like that. So this is what Famia called the closed form expressions. I, for simplicity, usually call them just the explicit solutions in plus times algebra. And for the exact same operations we had before, if we, and this is the point again, restrict our curve shapes to token buckets, this time the gamma RB notation, and rate latencies, we can simplify, and you probably have all seen that, so that solution. We can define the resulting curves using plus times algebra. The thing then is, each of these expressions here on the right side of the equation side is differentiable. And then if we compose all these operations and do the explicit closed form solution, so we get a term, a function that is also differentiable. What we now want to do is we want to optimize, right? I said I want to derive a configuration. So it's again an open parameter we want to set. So imagine one of these parameters is open and we want to find best values for this parameter. So we have that open, differentiate after this parameter, and then put it into a solver. That's basically the tool chain that produces the empirical results at the end. Now, I said we illustrate on the problem of finding best paths. When there are different paths, alternative paths that can be taken. For that, we simply generalize the model a bit. Imagine these two paths, I call it the above one and the below one, and they can both be taken by this flow F1 in version 1 or 2. And this is an exclusive OR. You can only take one of the paths. You don't want to have both in the analysis because that would give you two bad bounds, because it would assume traffic where there is no traffic. How we do that is by a new variable, the PFIJ. This is simply for each potential path, for each flow, a binary variable. And the sum of all binary variables for these flows should be 1. Therefore, only one flow is taken into account. Also, this is then used to get the arrival curve of the path. We do not take out of the picture, out of the analysis, because path not taken means this is 0 times 0, and the arrival curve is gone. Then we can differentiate after these parameters. Problem now is, this is a nonlinear program with mixed integer mixed in. So this is also very, very hard to analyze by solvers. What else do I have here? That's what I said, differentiate according to the flow's path to these p variables. So what then happens is, what in the paper, a trick is relaxation of the variables from binary to continuous variables. And here I reassured, got back to Fabien, that this would not mean, because the solver is smart enough, we get the solver's intelligence in here, would not mean we take partial delay bounds in the objective function. So that still works, makes the problem solvable without binary variables. And other than that, what we see here is optimization. We have an objective function. Here, what we have is, put simple, you see 1 divided by the amount of flows. It's the average of the delay bounds. But there could be other objective functions as well. We could define a utility function and put it into the objective of the optimization, or go for the maximum delay bound. All possible. under these conditions. So subject to the relaxed variables plus still the sum must be 1. It's handled by the solver that we do not have fractions. And what else do we have? Here, this is stability constraint. So the incoming rate does not exceed the server rate. Plus, this one is also an interesting part, more than this one. We can put in external requirements for the delay bound. So upper bounds that are required to be not overshot as additional constraints. And this then can be, if the delay bound expression is differentiated, optimized with gradient-based optimization techniques. Now we have these ideas of how to find parameter settings for open parameters. We have this tool chain, and we're putting it all together. So this is the practical part, the part where we needed to invest into the tool chain to make everything scalable, to make things faster. First idea was, and this is kind of a word of warning, just use Python, the SymPy library, go for the closed form expression. And what happens is that does not scale. So in the endeavor to find good tool support for differentiation, Fabia found automatic differentiation with computer algebra called CAS-ADI. It's quite recent, a 2019 paper introduced that tool. Tool is online available for use, and this differentiates these expressions quite efficiently. Now we have these. The first step, we have a tool that differentiates our expression. Second step is we need a good optimization algorithm. We found out that SLSQP, quite an older known one, sequential least squares quadratic programming, was good regarding performance. But I will show you more in the numerical evaluation, showing you that these statements about solvers are founded, and you don't have to trust just this simple line here, simply because having these tool chains and interfacing the tools, we can use different optimizers, and we did so. This is kind of a bit the box plot showing what I described. We have the network in our new alternative path model. We go for compiling. Fabian adopted a differentiation. So we have the objective differentiated. We can also have the non-differentiated one with the binary variables and MI, NLP, and we can put that into a solving library, which in the end, as the optimized networks, according to our problem statement, gives us the best flow path. And while this is so easy, here, imagine a big network with a lot of flows, as in the motivation in the first slide about the contribution, there was mentioned 1,000 flows, and they all having multiple alternative paths, so the combinatorial aspect explodes. There are some numbers about our evaluation set. So we went for a maximum of 18 servers and 21 flows, with virtual flows 45. So you see a bit more than, on average, 2 virtual passes to choose from. And these are then the overall path combinations. I told you they explode. So quite big numbers, up to 10 to the power of 5.52. That's what we call the simple networks. And then to check if we can scale even further, there are more complex networks, and just look at this number, the path combinations going to 10 to the power of 229. So the brute force approach is definitely not applicable to the more complex networks anymore. Neither was the mixed integer linear programming. I showed you the initial plot where it doesn't scale too well. So for the larger network to have some benchmarks, what we did, we randomized the search, so just randomly taking the passes. We benchmarked against shortest path, which is often used, and some meta heuristics. Again, this we can use a library, and the library provides us with some heuristics, some optimization methods that we use. Dataset, by the way, is available online in Fabian's GitHub repository. All right. The metric again, how close are we? Like before, a relative gap, defined a little bit differently. And, oh, no, that was wrong. How close are we? We can get really close and really, really close with two different versions, without restarts and with restarts. So to make a connection to the previous talk, there might be local minima we might be stuck in. Therefore, what the evaluation does, it says we allocate a 1 hour time limit for the optimizations, and if one run of this tool chain is faster than 1 hour, we just start it again with a different starting point to maybe circumvent these local minima and find a better way, find a global optimum. And the statistics on the small data set show that we are quite efficient with that. We find the optimum with these restart points quite often. So that was the slide I showed too early, but unfortunately, now let's see what happens. The average relative gap to the best value of the objective function. So on the small networks where we know that. Oh no, wait, this is among all optimization implementations, the best one we found, and then categorized by analysis, how far is the analysis on average of. So meaning that what we said is the best one, what we found out, as the relative gap is larger than 0, it means sometimes one of the other analyses find a better result. Sometimes maybe we were lucky with a random search and the big amount of settings. This is quite uncommon. What might have had a good result sometimes is this here, this Bonmin. This is actually not using the relaxation, so this is really using the binary variables, and we don't have to depend on the solver being smart enough to, in the end, just have binary weights. And I don't want to go into details with all the optimization methods. It just sticks out that this SLSQP gave the best performance, the bounds were the best. Whereas this is the other color here, red, these are without differentiation. We have the particle swarm optimization or artificial bee colony provided by some library. Turns out they are not that good. The delay-based shortest path, so not quite Dijkstra, but factoring in how the delay would be for a flow without interference, is even outperforming these NLP solvers. And of course, random and a search approach here that was not tailored like before, they perform not that well. So SLSQP, after having differentiated, looks good. In terms of delay bounds, second question, as always, the y-axis of the plots. How fast is it? The shortest path is, of course, the fastest. No surprise in that. And random sample with a small sample size is also super fast. Interestingly, this Bonmin is also fast, yet not that much faster than our SLSQP that by this empirical evaluation we found to be actually the best candidate to optimize for this problem. And this is exactly now the revelation, more detailed version of this plot I had in the first slides, where this blue line with some percentiles, it shows our DiffNC's performance regarding execution time. And you see, as I said here, all this differentiation going through the tools. So we're looking for the most efficient tools. It still has a penalty, but up from a size like, let's say 20, it is quite certain that it will be faster than a ULP formulation that is to be solved with Cplex, whereas we saw in my previous talk, Cplex might be slow. There might be the problem here again as well. And that it doesn't scale further up there is due to this 1 hour time limit that we allocated. So we will not have to wait forever for results to come in. Now this is this talk. Can already conclude. So what we did is we found a way inspired by machine learning, what's done there to put their tools as differentiation of the delay bound equation to network calculus. And we can actually, and that's what I emphasize, do much more like priority assignment. We just have to reformulate in the model. Just put these binary variables to denote priorities, then get the bounding equation according to a priority-based analysis. Packet schedulers, of course, as I said, the parameters, weights in round-robin schedulers, for example. For time-sensitive networking, I'm not so much into the details of that. I often see that there's underlying at the very basis is a TDMA service curve. And of course, that has, so this is for the gate control list, that has parameters, the cycle length, and the part that the queue gets from that cycle. That could be optimized if we can establish a theory to differentiate the expressions that are created by the analysis, meaning moving from min plus algebra to plus times algebra to feed it into the analyzer. This one here, I admittedly don't understand that well. Through end-to-end backpropagation in machine learning to get the weights for the neural networks. So if you have questions about that, please ask Fabien, who is the expert in this optimization. There I cannot help you, unfortunately. What I can help you with is to locate the work. The data set, as mentioned before, is in Fabien's GitHub repository. The paper was published at Infocom and should be in the IEEE Explore already. And as it was asked before, this was done with a proprietary toolchain by Fabien. This is not online in my repository. So here the code is not yet public. And I'm currently not aware if Fabien wants to put the code public or not. So please refer to Fabien and motivate him to do so. I would appreciate that too. Yeah, that's only the references coming. What I want to talk about, what I want to show you. So thank you for your attention. I take questions, of course.
I think we have time for one question.
Please. Oh, wait a second. Here's the microphone.
Thank you. The network calculus you showed, it produces differentiable results because you don't use line shaping and detail things like this, right? So what would happen if you use line shaping, or if in general, if you have only subgradients and not full gradients?
Good question. Admittedly, I'm not too sure about that. If you use line shaping, would that not simply introduce a maximum term in the equation? So you probably split that up in the differentiation. That would be my best guess. That
I think the derivative will have a discontinuity.
So if the derivative has discontinuity, yeah, I think you need to go for splitting it up in different cases, and that increases the complexity and will make things scale worse. It's my best guess. But yeah, we have not explored that yet due to the lack of our tool support for more complex curves like the staircase curves. Thank you for that comment. That's quite something to put on the future work list.
I think there is another question online.
Yes.
Just a second. Here's the microphone.
Is the optimization problem an integer optimization problem or a continuous one for path selection?
Yes. Yeah. That is when introducing these binary variables, it is it is an integer optimization problem, but the relaxation of these binary variables makes it a continuous one. And that's where I reaffirmed with Famia that he checked and that the solver is smart enough to really, in the end, put out binary weights. So this is kind of the magic that's happening in the libraries.
All right. So let's thank the speaker again and